This lesson is on related rates, which is one of the more applicable uses of calculus that we've studied so far. Sort of combines the ideas of implicit differentiation and the chain rule to relate rates of different things to each other, hence related rates. Let's see what that means. In this video, we're going to look at two different things. Ha! I learned how to write super neat. Check it out. So we're going to learn how to relate the rate of the change of one quantity to the rate of change of another quantity. Now, notice that I say rate of change and rate of change. A rate is sort of like a slope, and when I say slope, you think derivative. So really, these are going to be time derivatives because it's a rate of change with respect to usually time. 99% of the time it's going to be time. Get it? 99% of the time. Never mind. Anyway, so we get the idea of related and then rates. And to help us do this, we're going to use implicit differentiation and the chain rule, our friend, to help us out keep things straight. The following is an example of an easy related rates problem. The problem statement is this. Suppose that y equals x plus 3, and by that I mean x squared plus 3, and x and y are both functions of t. That means that they both change as time goes by. And we want to find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Oh my gosh, there's a lot of information going on here. Let's try to figure out what it's saying. Alright, so we know we have some sort of equation. We have the equation y equals x squared plus 3, and I know that I have to find dy dt. And I know that x is going to equal 1 at some point. Now you might be tempted to do this one of two ways. The first way that I will show you is wrong. Please don't do it this way. It's wrong. The way you do it wrong is you plug in 1. Great. Y equals 1 squared plus 3. So therefore, y equals 4. Oh, and then I have to find dy dt, so I take the derivative, and dy dt equals 0. No, that is wrong. Don't do that, or I will cry. The right way to do it essentially just reverses those two steps. Instead of plugging in 1 first and then taking the derivative, we're going to take the derivative first and then plug in 1. Now, when we take this derivative, be very careful. Watch me closely. Okay, you have y, no, not squared. Y equals x squared plus 3, and now the derivative that I'm taking is with respect to time. And because I like you guys, I'm going to color coordinate everything for this problem. So, the derivative that we're taking is with respect to time, and time is different from y, and it's different from x, so they all have their own special little colors. Awesome. Now, when we do this derivative, again, watch me closely. The first thing we do is dy dt. Well, that's just dy dt. Great. On the other side, check it out. I have to do the derivative of x squared and the derivative of 3. Now, the derivative of any constant is 0, so I'm going to ignore that because the derivative is 0. And now when I do the derivative of x squared, again, watch closely, I'm going to do the power rule, so I'm going to bring down the 2, and then there's an x, but don't forget, I have to do the chain rule because these variables do not match. Okay, so I'm going to end up with a dx dt at the end here, like that. So this is my correct derivative. Okay, I'm not done yet, I'm just showing that that's the correct derivative. Now we're going to go to the next slide and see what the heck this means. Alright, I have this equation. It says that dy dt equals 2x times dx dt. Now, in related rates, we do have to convert between math and words. This is very clearly math, because it's got like symbols and equations and stuff. And to convert it to words, here's what this means. Dy dt is the rate of change of y with respect to t. And t is time. So the rate of change of y with respect to time is equal to 2x times the rate of change of x with respect to time. I'll move it down here so we can see it. So essentially, the way that this short, nice little sentence works is that it says the rate of change, so rate of change of y, that's the dy dt, or rather with respect to time, that's the entire dy dt, is equal to, that's the equal sign, 2x is there, and then 2x times the, quote, rate of change of x with respect to time, that's the dx dt at the end. So in related rates, we will convert a lot between words, because a lot of times problems will be in word form, and you need to convert that to a mathematical equation that we can then work with. So essentially, the thing to get from this is that a rate of change is a derivative. So it's ddt of blah, whatever the function is. In this case, it's x and y. Other things, it might be different. Right, let's go ahead and answer that question. So back here, we had suppose y equals x squared, blah, blah, blah. Hey, we need to find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. So let's take those two pieces of information and answer the question. Right, the rest of the problem statement said that we need to find, ooh, I can move that. That's exciting. We have to find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. So really, there's only two more pieces of information, and guess what? They're right there, and we need to plug into those in order to find dy dt. Great. So at this point, it's really easy. We just plug in the information. So we have dy dt equals 2. X is 1, because it tells us that, and dx dt equals 2, because it tells us that. So dy dt is 4. And really, that's the answer to this problem. It took a while because I wanted to explain what all of it meant in terms of words and stuff in English, but this problem is algebraically and calculusally simple. So yeah, there you go. Enjoy. Oh, by the way, this is a rate, and so we might want to tack on units. If there are no units specified, it's going to be units per, I guess, second, maybe? Or just units per time. It should say. Most of the problems that are related rates will specify specific units, so just keep that in mind. Let's do an example of a medium difficulty related rates problem. Here's the problem statement. This problem is what's known as the falling ladder problem. And it goes something like this. You have a ladder. The ladder is leaning against the side of a house or a wall or something, and the base is being pulled away from the house or wall at a rate of 2 feet per second in this case. And the question is, how fast is the top of the ladder moving down the wall when the base is 7 feet from the wall? Alright, for any related rates problem, you need a good picture. And we'll practice drawing lots of pictures in class, but let's go ahead and draw a picture. Here's the wall, and here's the ground, and then a ladder is straight, and it's just going to lie like that against the wall. Great, there's my ladder. And let's go ahead and label some stuff. This is 10. And now, when you read related rates problems, you'll get a sense for the phrases and the vocabulary that they're using. One phrase here is that the base of the ladder is being pulled away from the house. Look at that, at a rate, rate, that's a key word, of 2 feet per second. That means that this end in blue is being pulled this way at a rate of 2 feet per second. Hey, rate. Rate is like slope, and when I say slope, you think derivative. Great. So that means that this length is changing at a rate of 2 feet per second. Let's call this length something. I'll call it x. And if x is increasing at 2 feet per second, that means that the rate of change of x, see that? Rate of change of x is 2 feet per second, and the rate of change of x with respect to time is dx dt. Therefore, 2 feet per second is dx dt in nice mathy terms. Excellent. Well, let's see, what else do we have? How fast is the top of the ladder moving down when the base is 7 feet from the wall? Now, you'll often see this phrase when, and that means that, hey, x is going to equal 7 at some point. At some point, not right away. Remember, there was a wrong way and a right way. If you plug in 7 right away, that's going to be wrong. So you have to wait. Wait, it's going to be okay. I got you. All right. So we have x equals 7 at some time. That's going to be after we take the derivative. But we also want to know how fast the top, that's here, how fast the top is moving down the wall. Great. We need to find another variable. Let's call this one y. Why? Because I said so. Great. And the quantity that we're looking for is how fast. How fast? Oh, that's also a rate. It's the rate of change of y with respect to t. So we want to find, essentially, dy dt. All right, so I just want to point out that this problem had almost no math in it. It had like 3 numbers. But from the problem, we're able to figure out that we need to find, essentially, a derivative of some changing relationship between the rates of x and y as they relate to this problem. So let's go ahead and do this problem so you can see how to do it. In order to solve this, I'm going to go through a process. It's about like 4 or 5 steps. You might have to use more depending on the problem in order to solve almost any, related rates problem. Here's the process. Here are the steps. Step 1 is almost crucial for any relates problem, and you have to draw an accurate picture of what's going on in the problem. If you don't, you might get messed up. Some problems require a picture so that you can see geometrical relationships and that sort of thing. We'll see that later in the problem that we're about to do. Step 2 is going to be identify what things, what variables, what quantities in the picture in the problem are variable. Variable means that they can change. I meant to underline that. Variables mean that they can change, and constants are things that stay the same. So in the picture, you want to figure out, okay, does this change, or is it a constant? Step 3 is to write an equation. That's better. An equation relating the variables to one another. This is going to be the related part of related rates. Basically, we want to get some formula that we can use, either like a formula or geometrical relationship or something that we can use to relate the variables. Awesome. Fourth thing you're going to do is the rate part of related rates, and you're going to take the time derivative of both sides of that equation in order to get those rates and an equation that relates those rates, hence related rates. Step 5 is, after you have that, you're usually just going to plug stuff in that you have in order to solve the problem and answer the question, and then after that you can do step 6, which is win at calculus. Awesome. Let's do it. So let's go through each step with our falling ladder problem. Step 1 was draw an accurate picture. So here's the wall, straight wall, that's better. Here's the ground, and here is the ladder. Great, accurate picture. Maybe if we wanted to label that as 90 degrees, we can. Ooh, that might help us later. Cool. Step 2 was identify any variables and constants. In this case, it's basically labeling the picture. In the picture, we know that the length of the ladder is 10, and we said that, let's keep it with our color scheme, the length of the ladder is 10. We decided to label the distance of the base as x and the distance of the height as y. And now let's identify which is variable and which is constant. 10, the length of the ladder, doesn't change. So this is a constant. I'll just abbreviate constant. And then x and y are both going to change, because if you imagine the ladder like falling down like this, very clearly both the distance and the height are going to change. So x is variable and y is variable. Great. Now we're done with step 2. Step 3 was to write an equation relating the variables. Can we see the relationship between x and y? Well, they're both legs of a right triangle. Oh, right triangle. Very nice. So I'm going to Pythagorize this. Bam. How nice is that? Okay, step 3 is done. Step 4, take the time derivative of each side to get the related rates equation. Cool. There it is. So let's do each part. Notice that on the right side here, 10 squared is 100, and 100 is a constant, so the time derivative is 0. So that's nice. That right side is going to be 0. And on the left side, notice we're going to use the power rule and then the chain rule. So we're going to bring down the 2. We're going to have 2x, and then the derivative of x with respect to t, because again, these variables don't match. And then we're going to do the same thing with y. So if you can imagine, well, we're going to bring down the 2, and then the t and the y don't match, so that's going to be another dy dt. Great, that's the end of step 4. We now have an equation that relates the change of x with respect to t to the change of y with respect to t. Now, this is a good check. Whenever you're doing a related rates problem, every single term probably should have something that changes with respect to t. Because if it doesn't, if it doesn't, that means it didn't change with respect to t, so it was a constant, so it should be a 0. Otherwise, it should have d something dt in it. If it doesn't, you did something wrong, go back and check. If it has two things, that means you killed a kitten and did the product rule incorrectly. Go back and check your work. We're now at step 6, which is plug in everything to find the answer. Now, the original problem said that the distance was 7 feet. I'm going to change that to be 8, just to make our equation a little bit nicer. You'll see why in a second. So let's go back. Right, so we're going to plug in. Let's do it. 2. Hey, x, we just said x is 8. Now is when we plug that in, after taking the derivative. Awesome. dx dt. I remember reading or hearing something about dx dt in the problem. Oh, right, we said that because the bottom was moving away at 2 feet per second, dx dt was 2. So it's 2. Great. Plus 2 y and dy dt. We're not quite done yet, and we can't win at calculus, so we're sad. Okay, so we have 2 unknowns left. One of them is the thing we want to find. That's okay, but we have this pesky little y that's just hanging out there. We need to solve for it. How do we do that? Oh, look at that. Look, up here. We have an original equation, and the original equation relates x and y with nothing else. That's very nice. And guess what? We know x. It's right there. So you're going to plug x into that equation and solve for y. Now, if you're noticing and paying attention, this is a 3, 4, 5 triangle that I multiplied everything by 2. And so if x is 8 and the hypotenuse is 10, that means that y is 6. Great, y is 6. If you didn't follow that, plug it into the Pythagorean theorem and find out. Cool. Let's now solve for dy dt. 2 times 8 times 2 is 2 times 8 is 16. 16 times 2 is 32. Excellent. And I'm going to move that to the other side, so it's negative. So negative 32 equals 2 times 6, which is 12 times dy dt. Dropping the colors now. And now we can solve for dy dt by dividing. So dy dt equals negative 32 over 12. Simplifies as negative 8/3. And let's throw some units on that. Remember that it was feet per second. I like seconds. Feet per second. Excellent. I know this is long. We're almost done. Just want to notice something very special about this number. Notice that the change of y with respect to t is negative. Does that make sense in the problem? Go back to the problem. Here's the height, and the height is, in fact, decreasing. Because the height is decreasing, that means that the rate at which the height is changing should be negative. Congratulations, you have just now